All right. Thanks, Pat. Thank you, everybody, for having me here. It's looks like I picked the right time. It's really beautiful here, and I'm looking forward to sticking around today and tomorrow. I'm going to be talking today about some work I've been doing at the CFA with Lars Hörnquist and TJ Cox primarily. As Norm was just pointing out, there's a pretty large group of collaborators there affiliated with Lars's group who've all been a big part of this. In particular, Dushan Kures and Brent Robertson and Paul Martini and Adam Leeds, Volker Springel, who developed many of the codes I'm going to be talking about, and a number of others who've been parts of lots of different aspects of this throughout the last couple of years. And I'm going to try and paint sort of a very broad overview of the work we've been doing. I know a lot of the people here don't necessarily work on quasars and galaxy formation, so I'm going to try and paint the big picture, why this is interesting, and where we think this field is going. So to begin, what's the general motivation? Why do we care? And in particular, why have AGN and AGN feedback become such a buzzword in galaxy formation? And we now know that since HST in the last decade or so, every massive galaxy appears to host a supermassive black hole. And from very basic arguments, Sultan 82 showed that more or less you can estimate the black hole mass budget by just integrating up the luminosity density of quasars, assuming some radiative efficiency. And if you compare that to what's observed, you more or less get the answer that all these supermassive black holes had to gain most of their mass in relatively short-lived, high accretion rate phases as quasars or luminous AGN. And so this is just one of many ways of showing it. You don't need to decode what all these points are, but there's many different ways you can try and show that yesterday's quasar is today's big elliptical or massive bulge. This is from a paper comparing clustering observations. The only take-home point here is that these colored points are, if you just take where all the observed quasars cluster and evolve that forward in an n-body simulation, not only do we see the supermassive black holes living in galaxies, but given where we see quasars live at high redshift, their remnants live exactly where elliptical galaxies live. Half of these points are how ellipticals cluster as a function of their mass. So essentially, today's elliptical was yesterday's quasar. You can show it in a number of different ways. And I would argue the most compelling way is a plot that probably everybody's heard of, if not seen, which is the M-sigma relation. And so the idea is that black holes are somehow sensitive to their host galaxy properties. So here's black hole mass, which is relevant on very small scales. Even if I were to consider where this is gravitationally important in a galaxy, that's a scale of maybe a few parsecs, maybe 10 parsecs. Compared to the characteristic stellar velocity of the galaxy, the velocity dispersion measured on scales of kiloparsecs. And there's this very tight correlation. Another way of saying this is black hole mass versus the mass of the host stellar bulge. You get a relation that says that black hole mass is about a constant fraction, about 1 part in 1,000 of the host bulge mass, with a scatter of a factor of 2 or so. So this little blue arrow here is about the observed intrinsic scatter in this relation. Now, if just from very simple models you say how much scatter is there in the amount of mass over the lifetime of a galaxy or over a population of galaxies, how much gas gets down into the gravitational radius of influence of the black hole, or even in the local universe, how much gas do we observe falling into where the black hole should be able to capture it? And the scatter in that is a couple orders of magnitude, basically. It's really easy to knock, say you have some collision that happens to strip angular momentum from the right couple giant molecular clouds. You knock 100 times the black hole mass down into the center of the galaxy, into the black hole's radius of influence. It's very easy to do that. So why doesn't the black hole shoot up? Why don't we see black holes that lie a factor of 100 off the relation? How do they know to stop at just this very narrow range? And that has led to the idea that black holes must somehow self-regulate. Essentially, in order to maintain not just the normalization, but the very small scatter in this relation, black holes have to have some ability to stop new gas from coming in.
What seems a small scatter there? Because a number of the points are factor 4, 5 above or below that line.
So first of all, a number of these data points have since been updated. And if you look at the observational error bars, they're consistent with an intrinsic scatter of less than a factor of 2. And if you update this with newer data, I mean, you more or less, the estimated intrinsic scatter in all these correlations has been, between 0.2 and 0.3 dex from the simple estimate you get with these earliest data sets all the way through the most recent data sets that have smaller error bars and many more points. So I promise this will be the most text on any slide I show, but I just want to give the basic argument for how this could arise, due originally to Silk and Rees 98, although there's many papers since then. Norm, for example, has a paper where you can derive more sophisticated versions of this, but they all boil down qualitatively to a very simple, similar argument. So you've got some luminous accretion disk. Mm-hmm.
What were the predictions for the scatter before that?
Well, so before, nobody knew if every galaxy would have a black hole. And if you naively just assume that the black hole is formed by how much mass you can randomly trickle down to the radius of the black hole, you'd expect between 1 and 2 orders of magnitude in scatter.
What I would say is it hadn't occurred to anybody that there ought to be any relation between M and sigma.
Yeah.
So there was no prediction.
Yeah. Nobody was actually making predictions. If they had, they probably would have expected it to look largely like a scatter plot, maybe broadly more massive black holes in more massive systems. But nobody even came close to expecting something this tight. And so, if you've got some black hole accreting at m dot with some radiative efficiency that basic physics tells you is something like 0.1 to within a factor of a few, you've got your luminosity. The total energy radiated will be that 0.1 or so radiative efficiency times the black hole mass times c squared. So in a typical 10 to the 8 solar mass black hole, L-star elliptical system, that's 10 to the 61 ergs. That's just the luminous energy of this thing while it was accreting. So then compare that to the gravitational binding energy of the of all the stars in the galaxy, or stars in dark matter. You get galaxy mass sigma squared with some coefficient that depends on details, which works out to be about 10 to the 59 ergs for the same galaxy. So in short, if only a few percent of the luminous energy of the black hole can couple to the gas in the galaxy, it would unbind it. So you can turn that around and say if some fraction, say a few percent of the luminosity, can somehow couple effectively, either energetically or say some of the momentum in this luminosity can couple, then accretion has to stop when you reach this threshold. Gas can't keep raining down on the black hole if it's had more than the binding energy or been accelerated up to past the escape velocity. And so if it's a few percent, then that predicts that black hole mass should go as this mess of constants times galaxy mass, which works out to be, for a few percent, about 1/1000th of the galaxy mass. So in other words, this can explain this relation and its narrow scatter, because the black hole is forced to stop, essentially. Accretion is forced to stop when you reach this threshold. And once you open up this possibility, then all of a sudden this feedback energy is very exciting from the perspective of galaxy formation, because it can affect lots of things: star formation, cooling, the colors of galaxies, and their subsequent growth. And one important point to make, it's absolutely unclear observationally what the most effective forms of feedback are. What are the feedback processes that matter for setting the M-sigma relation? However, that's not to say that we don't see feedback, that we don't have any evidence for AGN feedback. In fact, the problem is that there's far too many candidate forms of feedback that we see. We know that many galaxies have radio jets coming from the AGN. We see winds that are presumably launched off the accretion disk. We see them basically at a large number of scales, anywhere from, it's been observationally estimated, from literally the accretion disk scales all the way out to hundreds of parsec scales. You've got, we see the luminosity of the AGN, and we know that there has to be some radiation pressure associated with that can drive winds. We know that Compton heating is important in some radius around the black hole, and we see AGN ionizing huge volumes around their galaxies. So all of these forms of feedback are involved, and it's really a question of how do they then affect the galaxy on global scales. So there's other tentative suggestions that this may in fact be coupled to things like star formation and you may actually be able to use that feedback to do those other things I suggested. So one possibility, this is from a paper with Adam Leeds, although we did a similar calculation in a paper with Kevin Bundy here. If you compare the mean time when black holes of a given mass form, so if you just take the black hole mass function observed today, the quasar luminosity functions, and integrate the continuity equations for black hole mass under some simplifying assumptions, sure, but you can show the answer doesn't depend too much on those assumptions. You can derive roughly when do black holes of a given mass accrete most of their energy, or most of their mass. So this is the look-back time when black holes of a given mass accreted, say, half of their present mass. The black line is the median, and this is the dashed lines are the scatter. Just from this simple scaling argument, many people have done various versions of this, Salucci et al., Ewan Tremaine, et cetera. Now compare this for the ellipticals that these black holes live in today. We can just measure their stellar population ages. Roughly, when did star formation in these systems stop? And that's what these colored points are. In the host spheroid mass that corresponds to this black hole mass, what's the mean stellar population age? And the error bars are the scatter in ages at a given mass. So the two line up right on top of each other. And there's many other ways that you can make this same argument that all seem to favor, that all seem to point to the fact that black hole growth and star formation shutdown in bulges are coeval. Now, it doesn't say that this is a causal relationship, which is something that is still fairly ambiguous, but at least whatever process happened, processes caused these had to happen about the same time. Now, there's a lot of other suggestions in models that this is important and can explain other long-standing problems. For example, this is the color magnitude diagram of galaxies, stellar mass versus B minus V color in a model by Darren Croton. Here's his sort of standard prediction without any AGN, and you get this big population of very massive, very blue galaxies. Essentially, all the massive galaxies, and this is a problem not particular to Darren's, but endemic to everybody's models, all the massive galaxies are still forming stars far too actively. As well, if you compare the galaxy mass function to the halo mass function, I've just rescaled them horizontally by some arbitrary amount, galaxies have this sharp break above L star. Halos keep going to much larger masses. So galaxies somehow stop cooling new gas in and forming new stars. And so invoking various forms of AGN feedback, which is what's shown in this upper panel, you can potentially solve this problem. Now in practice, the kind of feedback that's invoked here is different from what I'm actually going to focus on in this talk. Here, you want something that can stop cooling, which is largely happening over a Hubble time. And so this leads to the distinction between what some people call bright versus radio mode or quasar versus radio mode. You could call it transition versus maintenance mode feedback. So I'm going to focus in this talk on what I call the transition mode feedback. This is what's associated with the movement of mass from the blue cloud to the red sequence. If there's feedback associated with what I said where star formation shut down the same time black holes grew most of their mass. It has to happen quickly. We don't see many galaxies slowly trickling from red to blue, or from blue to red. It has to be relevant on small scales because it has to halt the growth of the quasar itself to give you, of the black hole itself in order to give you the M-sigma relation. And if you want it to affect the galaxy, it's got to happen in the galaxy. It's probably associated with this quasar mode because that's where black holes gain most of their mass. It's presumably associated with morphological transformation because those systems that are blue that are still star forming are almost uniformly disks, and all the systems that have stopped forming stars are almost uniformly ellipticals. And so all of this, as well as other arguments, lead us to the conclusion that gas-rich mergers are a fairly viable candidate for where you might see this sort of feedback, for where this might be important. The other mode of feedback that I won't talk about, but I want to outline because it's just as important for a lot of aspects of galaxy formation, is the maintenance mode feedback. This is where you try and explain how, once you've made a red galaxy, once you shut down star formation, say this happens when you make the elliptical at z of 2 and when you form the black hole, now you've got to keep it red for 10 gigayears. So this is something long-lived, lasts for a Hubble time. It has to affect gas cooling on large halo-sized scales. This is what people call radio mode because we often see radio jets in these systems, but really whenever you hear the word radio mode, from the theorist side, we really are more using it to refer broadly to low accretion rate feedback, because in these ellipticals, you don't see many bright high Eddington ratio quasars. If there's any morphological changes here, they're subtle, probably related to subsequent dissipationless merging of slamming two ellipticals together. So there are connections potentially between these, which I won't have time to get into, but it's important to remember that there's no reason these should be the same mechanism, sort of prima facie.
Do you think the maintenance mode is connected to the black hole at all?
So there are some arguments that you may not need a black hole at all to do this, that other just dynamical effects, for example, can give it to you. Those models are pretty hard to get to work in detail, and it's yet been really demonstrated in a simulation that any non-black hole feedback is sufficient for those. But I think it's an open question. So don't bother trying to read the small text here. This is just a figure sort of outlining a very general scenario in which all of these things tie together. So this is a time sequence of star formation rate and AGN luminosity, where 0 is a merger, and just different sort of stages of galaxy life highlighted, focusing on the stage that I'm going to spend the rest of the talk on. So you begin life as a galaxy as an isolated disk. You're going to grow considerably due to accretion. The halo mass is going to grow. You will have AGN activity here from various processes, bars, minor mergers, just random events. But it's pretty hard to grow a black hole mass above a few times 10 to the 7 solar masses, for arguments I'll come to. But eventually these systems are going to get accreted into groups. They're going to have interactions and start merging. And then you'll have this final stages of the merger where two galaxies coalesce. And if it's a major merger, you funnel gas into the center. You get something like a LERG or a ULERG with dense central gas concentrations and a buried AGN. If that AGN keeps growing and its energy or momentum can somehow couple to the gas, it'll eventually clear out what little gas may be left after star formation, and you'll have a visible quasar. Having exhausted the gas, the system will decay rapidly. You'll have a post-starburst elliptical with a low luminosity AGN that's fading onto the red sequence. And then you're left with a relatively dead elliptical. Whatever maintenance mode you like has to kick in now and keep this thing from allowing much new gas to cool and keep it from starting the whole thing over again. So there's sort of three big questions. How are these things, in terms of quasars, how are these things lit up? How do they behave once they're lit up? And how does that behavior affect the rest of the galaxy? There's a lot of sub-questions you can ask. And more importantly, I think all of these are not really separable questions. Of course, feedback may shut down the light curve. It may turn off the quasar. It may be that different modes of feedback are important for different triggering mechanisms. It may be that things light up differently based on different triggering mechanisms, etc. And because these are messy and fairly inseparable questions, we want to look at a process that involves basically as much mess as possible to study this. And so here we come back to this idea that, at least for the mode I'm interested in, black holes probably gain a lot of mass in mergers. And one argument is simply that if black holes do trace spheroids, then most of their mass is presumably added in mergers. The reason is that while it's not 100% uncontroversial, if you ask most people, how do you make an elliptical galaxy, they'll tell you major mergers. It's a lot less controversial to say that than to say, how do you make a quasar? But if indeed black hole mass tracks the bulge mass, as the observations suggest, if some relation like that is true at all redshifts, then the black holes have to be primarily forming, if their classical bulge hosts are, in mergers. And then the other candidate has to be similarly fast and violent, blend gas and stellar dynamics. And it's for the reasons I've given that you need to grow most of your black hole in this short-lived phase, as well as reorganize the stars by some violent relaxation to build your bulge. And you see some evidence of this locally. These are HST images of local quasar hosts by John Bacall. You see a diverse array of behaviors, but in particular, as you look at the brightest systems, you see a lot of evidence of disturbance in these things, and even a lot of objects that historically have been called quasar hosts that have been classified as normal or unrelaxed. Recent analysis by Gabriella Canalizzo and Nicola Bennett has shown they essentially all have evidence of mergers if you look at them long enough. There's also great candidate objects like NGC 6240. This is a picture from Kumosa et al. This is the optical image. It's a big merger mess. And this is a zoom in on the center from Chandra, where you see the two accreting black holes merging in towards each other. So again, this general story I've already outlined. The galaxies collide, tidal torques strip the gas of its angular momentum, and it can feed black hole growth and a starburst. So briefly, I want to touch on why am I going to ignore, although I will come back to the question of minor mergers and other forms of fueling. The reason is simply that it's harder to build up black holes this way, in particular the most massive L-star quasars that I'm going to argue do the most feedback. This is just a simulation of a minor merger. This is just a plot showing sort of what the expected numbers of minor mergers are. The punchline, though, is that, first of all, minor mergers aren't that violent, so it's harder for them to get gas into the center.
Gas on the left and stars on the right?
Yes, gas on the left and stars on the right, sorry. And secondly, even minor mergers aren't very efficient when you actually do the global calculation. That's what this is showing, is sort of relative rates of minor and major mergers. The point is simply, the punchline is just that even if you assume naively the optimal efficiency of minor mergers, i.e. that a 1 to 10 merger gives you 1/10 of the black hole growth that a 1 to 1 merger does, it turns out that when you integrate over merger histories of galaxies, the major mergers are more important. Yes, there are more minor than major mergers, but not so many more so that even with optimal efficiency, they'd win. Mm-hmm.
What is the thing that CDs have formed in major mergers, right? I mean, they build up by lots of somewhat smaller things. So how did the holes in
So I would So I would argue that CDs would start as more L-star galaxies on this relation at higher redshift, but then this is a broad statement. As a function of mass, once you're well above L-star, there's not many other well above L-star things for you to keep major mergers going on with. So your growth does start being dominated by a series of minor mergers. And that does have some subtle implications for how you move potentially off the M sigma relation. You'd expect basically to not move exactly perpendicular to it, but slightly off in the direction of having more massive black holes. And in fact, Carl Gebhardt is looking at some of these objects, and even some of the ones that were put on the M sigma relation, but doing more detailed models, and there may be some tentative evidence of that happening in the CDs. But I think there's so few black holes known in CD galaxies with measured masses that it's still open whether that's seen.
I'm sorry, is it tendency for what?
There's a tendency relative to M sigma for at the massive end the black holes get a little high, which is the direction you'd expect them to move off of this. So just to give you the sort of rule of thumb that comes out of simulations, this comes from a paper by Josh Younger, a graduate student I've been working with, who actually just put this on AstroPH a couple days ago. It's pretty hard in minor mergers, even assuming fairly high efficiency, give them even the optimal orbits, throw it in on a straight radial orbit so it smashes right into the center of a galaxy. It's pretty hard to build a black hole above a couple times 10 to the 7 solar masses. So these points are all simulated merger remnants. The colored ones are minor mergers, and they really cap out at a couple times 10 to the 7. And the reason is pretty simple. The black hole, it's not a function of how much gas you put into the center, this argument I made at the beginning of the talk. This is final black hole mass relative to bulge mass versus how much gas actually gets dumped into the very center in the merger. And there's just a scatter plot here. It's really what sets the black hole mass in these feedback regulated models is how deep the potential is at the center of the galaxy. The black hole, in this simulation, we've put in a very simple version of that analytic argument I gave you at the beginning, where the black hole just some fraction of its accretion rate couples to the surrounding gas. And if that happens, then the deeper the potential, the harder the black hole has to work, the bigger it has to get before it can unbind the gas. But that's the only thing that determines its mass, not how much gas actually gets into the center. And I can give you the same argument for why, say, disk and bar instabilities are very inefficient. Those things, it's very well known from studies going back 30 years, are not very good at building up very dense bulges with very compact potentials, very deep potentials. And so likewise, they can't help you build a massive black hole. Maybe they can get gas into the center, but it doesn't matter because the black hole doesn't feel a very deep potential and can immediately unbind all of that gas. And again, this is just confirmation of that in simulations. These colored points are the minor mergers, and with different gas fractions, it doesn't make a difference. You can't get above a couple times 10 to the 7 solar masses. So
what you're kind of not quite saying is to make massive galaxies,
to make massive bulges,
Lossy dispersion bulges,
yeah, you need
have a dissipated gas-rich merger.
exactly, yeah. So fundamentally, yeah, you need to build a massive black hole. You need to build a massive bulge, and these other mechanisms aren't very good at doing that. But I think that's an important point to make because traditionally people have only worried about the problem of getting the gas down to the center, and it's more than that. So the sort of broadly emergent picture is something where different mechanisms dominate at different luminosities. This is the z of 0 AGN luminosity function, and if you translate that a couple times 10 to the 7 solar masses to a luminosity, it's something actually remarkably close to the traditional Seifert quasar divide of a minus 23 or so in B band, where you'd expect minor mergers and things in more disky hosts to dominate versus needing to invoke more violent mechanisms that build up a bigger bulge component.
I think even in some of your papers you might have mentioned pseudobulges.
Mm-hmm.
Are these ever significant enough? I mean, these are things that I guess they're observationally largely indistinguishable from the classical bulges?
So they are, if you have detailed observations, you can tell a pseudobulge from a classical bulge. So for those of you who aren't familiar, pseudobulge just refers to bulges made by these disk instabilities they're not as compact. They basically look like, puffed up disky type components in a lot of ways. And so we get pseudobulges from some of our simulations. Another way you can look at this constraint is just look, what's the mass function of pseudobulges in the local universe? And when you do that, it implies that their black holes are not very significant in the global budget, that the black holes in pseudobulges, so presumably black holes made by these mechanisms, are important only below 10 to the 7 solar masses, or even smaller.
So you're not claiming that pseudobulges have the same M0?
I'll actually come to that. I'll show you what our predictions are for that. I think there's actually a lot of interesting constraints that you might be able to get from looking at where they lie. So I've mentioned our simulations a couple times now. I'm going to take you through some of what happens in the simulations in a little more detail now. And I want to emphasize that our modeling of quasar feedback is very rough, and we're just trying to put in the sort of lowest order, simplest model we can because we don't know the details of how it couples. So we just say that, say, 5% of the accretion energy of the luminous energy of the black hole couples to the surrounding gas. And we just do it on the smallest resolution element we can in the simulation, which is comparable to the Bondi radius or so of the black hole. Now, very broadly, in practice, you get a similar answer if you calculate sort of what should couple based on line opacities given some AGN spectrum. If you assume that actually it's momentum coupling from the AGN driving on dust grains, again, by the time we get out to hundreds of parsecs where our galaxies are really resolved and we're measuring how this is affecting things, that doesn't make too much of a difference. Or if you assume, say, what's seen in simulations of driving of disk winds off of accretion disks. These are examples of simulations by Dan Proga where you get this strong wind launched off the accretion disk. If you just were to assume that wind smashes into something in the nearest 10 parsecs to the AGN, you'll get a similar answer. All these mechanisms will be qualitatively similar for most of the things I'm going to talk about. I think there are some very robust things you can say. The mechanism that what I'm going to talk about probably has nothing to do with is radio jets. Those are going to punch straight through the galaxy and be relevant on much larger scales. So again, we just resolve down to something like the Bondi radius. We'd really love to, of course, resolve the actual accretion, but it's a little demanding by a factor of 1,000,000 beyond what we can actually resolve. However, we can get down near the Bondi rate, or Bondi radius, so we'll just take the Bondi rate as our accretion rate approximation. Even that, it turns out, doesn't really matter for most of the things I'm going to talk about, because if you actually calculate the Bondi rate during a galaxy merger when all this gas is dumped onto the center, it's 100 times Eddington. So you just cap these things at Eddington, which all the observations suggest is actually a reasonable thing to do, and your behavior doesn't end up very sensitive to the details. So that having been said, let's look at what actually happens. So this is the projected gas density in a 2-to-1 major merger, times shown in the upper left. The color shows the gas temperature. So blue is 10 to the 4 Kelvin, all the way up through yellow, which may be hard to see on this screen. There was just a little puff of yellow here. That's 10 to the 6 Kelvin gas. So the two disks fall in. They lose angular momentum to the halo after they pass each other for the first time and coalesce. Now, in that mess, all this gas gets channeled into the center, and a combination of feedback from starbursts and quasar blows it out. Again, it's sort of hard to see in this movie, although, as always, it looks prettier on the computer. But let me show just again. You get this fairly explosive outflow. At least it looks explosive from these scales because the energy is all coupling on scales of relevance to the black hole, which are much shorter time scales, much shorter spatial scales than the kiloparsecs of the galaxy. So it looks like this sudden explosion. You get a little burst of activity after first passage because some gas gets funneled in. And I want to emphasize that while it looks like at the end the gas is completely obliterated by this, 90% of the gas over the course of this merger is turning into stars. So the amount of gas that actually participates in that outflow is only, say, a couple percent of the galaxy mass.
So you do the simulation, you have some gravitational softening with
Mm-hmm.
and so you're supplying your energy to just
Sorry, let me just say,
particles.
this is the corresponding movie watching the stars happening. Sorry to interrupt, but and color here, blue is younger stars, red is older stars. But you'll see the same dynamical process, but you'll just see that the stars are relatively intact and in place when this feedback event happens. So there's first passage, and as they come together, the bulge of the galaxy, the core of that bulge, forms very quickly and relaxes actually very quickly, so that the black hole is largely growing in a fixed potential background. So there is when the black holes coalesce. Right now is when that feedback blast came out. And it's largely happening in the background of a increasingly relaxed elliptical with very small tidal features here that, unfortunately, the surface brightness background is too big here. Sorry, go.
I was just trying to understand a little bit more in detail the actual feedback that you guys use.
Mm-hmm.
So you have some gravitational softening length, which is in a simulation like this, tens of parsecs, or
Yeah.
and then you assume that you've got some black hole that's accreting at Eddington. That gives you a certain amount of energy, and you impart that to equally to all the gas particles within the softening length of the black hole.
We just weight it by the smoothing kernel of the simulation. Yeah. And we've experimented with some other simple applications. Again, for the scales we're interested in here, it behaves more or less the same. You're dumping a lot of energy by the galaxy's standards into a very small radius in a very short time, no matter what.
You quickly build up, I guess, temperature gradients that then accelerate your gas.
Yeah, so in detail, this gives you something like a pressure-driven outflow. At very small scales, the velocity structure of this wind will be different from something that's, say, driven directly by radiation pressure, by momentum coupling to dust grains, or by, there's other ways that you can do this too. Compton heating will probably accelerate the wind at much smaller scales. Those are all details that matter in that small radius around the black hole, but not on the scales that you're seeing in this movie.
Even though you're dumping all this energy into the very center, your I guess heat transfer is enough to chase out gas at much larger distances?
Yeah, so it's able to couple fairly efficiently to larger scales. There are some caveats about that we can talk about later in terms of the details, the microphysics of the gas that we're not modeling here. Like everybody else modeling a whole galaxy, you have to treat the microphysics of the ISM in some approximate sub-resolution manner, and there may be a lot of mess in that.
Using Hilbert's usual funny equation of state.
Yeah, so we're effectively approximating all that by a different equation of state for the gas. You'd really love to move to a situation where you can resolve individual clouds, all of that, and we're getting there, but it's a difficult thing to do.
But basically what you're doing is the gas comes up to 10 to the 6 or 10 to the 7 K, which
Mhm.
means it's above the escape velocity. It sounds like it's comparable to
Yeah.
But there's some gas in the center that turns into stars.
Yeah, so the vast majority of the gas has already turned into stars when the AGN hits its peak.
What radius does the uniform stars dominate?
So I won't talk much about how that changes the how those stars contribute to the galaxy, although this is the topic of a set of papers that we've been working on, the first of which was on AstroPH a couple of weeks ago. The stars formed in the merger dominate within a few hundred parsecs, the light profile. And when you look at recent merger remnants, you can actually look in great detail as to whether the simulations are reproducing those features. So this is just a qualitative outline of what you just saw, star formation rate with different times labeled showing the gas and stars. I just want to highlight how short this actual active phase is in the grand scheme of things. And going from Ulurg to Quasar, the vast majority of the stars in the final remnant are formed before this time. Like I said, the stars formed in the actual burst even might dominate the profile within a few hundred parsecs, but that's only a few percent of the galaxy light. And even then, that exhausts most of the gas that's left. What's blown out by the quasar is really a small trickle.
So this was the gas fraction at the beginning of the merger?
So in this case, at this arbitrary initialized time, this was 40% gas.
Is that the star formation rate in the whole galaxy or just in the bulge?
That's in the whole galaxy.
And is the bulge proportional
So
to that?
no, so most of this is all happening in disks before the actual collision of things. So most of the stars you'd expect to be formed originally in disks and then violently relaxed collisionlessly.
So, but you said that if the gas fraction was 40% and you're turning 90% of that into stars, that's still a third of the stars in this merger, due to this merger.
No, 90% of the gas is turned into
That's
stars.
what I'm saying. And it's
Yeah.
40% to begin with the mass.
Mhm.
So that's 9 times 4 is 36% of the stars at the end were formed in the merger.
Well, only by the arbitrary time definition that the merger started here. In terms of actually being formed by gas that loses its angular momentum and gets dumped into the starburst, that is only 5-10% of the mass. Yeah, sorry. 30% of that, 30% of the mass, the majority of the gas that we start with in the simulation turns into stars over this time, where the two, you've got a little bridge here, but they're largely still disks, and they're really forming stars in those disks.
So let me ask you this then. How long, what fraction of the time that's solar mass is bigger as 10 to the 1 and 10 to the 2? So it's not even really a Euler except in that brief little phase.
Yeah, the Euler lifetimes you get out of this are quite short, maybe 100 million years. Depends, of course, on, that's the time above some cuts. So it's a very,
well, it's 10 to the 12, so it's 50 or 80 solar masses a year.
yeah.
Okay, so that's basically 10 to the 8 years, you said? 100 million years?
Very rough. I mean, it depends on, I can change this normalization by just cranking up the gas content or
Yes,
something like
that's
that.
what I was wondering about.
Yeah.
So that's a good question, right? What fraction in the world are formed in a Euler phase, and what fraction are formed in this phase?
In a qualitative sense, where if I define Euler less as a luminosity cut and more as a physical cut of what fraction formed by the actual starburst gas that lost its angular momentum and burst in the center, for an L-star galaxy, the answer is about 10%. And that number scales with the progenitor disk gas fractions in a way that's more or less logical, tracing how much gas those disks have. So observationally, at, say, 10 to the 9 solar masses, you might expect that fraction be as high as 30%. And super L-star, it could be as low as 1% or a couple percent. So I might skip this movie because I was going to show it because there's some beautiful low surface brightness features, but the room is not very conducive to it, and it's telling the same story. But if you want to see it, it's an example of what we can do when we add on top of this radiative transfer. You can see a little bit of this. This is a Mach 3-color image made by Patrick Jansson's Sunrise code, showed face on and edge on. And you can see, if you really squint from the back, dust lanes in the center and blue regions where there's star formation going on. But again, I think it's a little hard to see, so I'll just qualitatively outline what's happening when you actually add that layer. So this is the quasar light curve as a function of time. This is the bolometric luminosity in black, the observed B-band luminosity averaged over a bunch of sight lines in blue. And this is the column density towards the center that you get from just applying a simple radiative transfer model through the gas in the simulations. And the point is that you get moderate column densities over the course of the evolution of the system with some range due to angles. That's what this shaded area is. But then during this final stage, you have all this gas dumped into the center, your column density jumps up. And this, of course, when you see ULERGs in the local universe, they have enormous dust content, enormous columns towards their center. And that, you can see here, just completely takes the optical luminosity of the quasar out of contention. There's no observable optical system during this phase. And it's only in this last blowout stage where the 90% of this gas has now been consumed by star formation. What little trickle is left, it's basically a combination of factors. There's only a small amount of gas left because star formation's eaten most of it, and the black hole has been steadily getting bigger this whole time, so it's putting in more feedback. It's able to blow out that little bit of gas that's left, still obscuring it, and shine brightly as an optical quasar for this spike here. But now, of course, you've gotten rid of your fuel supply, so the black hole has sort of suicidally bursted. And
Go up. You say bolometric luminosity. Is that quasar plus star formation?
sorry, that's just quasar. Yeah, this is just quasar.
So you're saying you got a quasar luminosity plus 10 to the 13 is totally obscured.
Yeah,
In most of that phase.
yeah.
But you don't see that in nearby ULERGs or infrared sources.
Well, we don't see quasars with 10 to the 13 solar. I mean, this is a 10 to the 9 solar mass black hole at Eddington. So,
But you see nearby ULERGs which have luminosities above 10 to the 12.
mhm.
And the AGN luminosities are definitely well below that.
Yeah. So I think this thing would be a better analog to some of the brightest submillimeter galaxies, which have luminosities perhaps a factor of a few in excess of 10 to the 13. And while the general, it's very ambiguous how much of that is AGN. At the bright end, the consensus is that it may still be largely star formation, but that it's a non-negligible. I mean, if 30% of that is an AGN, that's more or less consistent with what we see. We're working right now on modeling in more detail during phases like ULERG phases, what's the relative contribution from obscured AGN and what's not, and how can we, using the simulations, design new tests observationally to try and go after that point.
These simulations are supernova free, is that right?
No, so we do include supernova feedback in a couple of ways. One is that it's effectively modeled in this sub-resolution description of the ISM. We also have direct stellar supernova-driven wind feedback, so basically just taking the lowest order approximation, say, with some mass loading, X times the star formation rate gets blown out in a wind. That doesn't change the story I'm telling for the AGN very much, because even the starburst at the center can't get rid of the gas that's right around the black hole. It's going to dump as much in as out.
How much gas was driven out by the supernova or stellar feedback, and how much in the simulations? That's divided up.
So if we put in strong supernova feedback, then in terms of absolute mass budget driven out by one mechanism or the other, more is driven out by supernova feedback. And that will largely contribute towards the hot halo, the same way that the AGN will. At the scales we're resolving, it's actually very hard to tell the difference in practice between something driven by the AGN and the star formation. Yeah. So
That's this number of sort of 10% of the gas.
yeah, that's related to how little of the gas is left when the AGN is going off.
But you could turn off the black hole.
Yeah. So if I turn off the black holes completely, if I remove them from the simulations, then almost nothing looks different except for the star formation behavior in that little trickle after the merger, which I'll come back to. But it's very important to have black hole feedback for the black holes themselves, which is what's shown here. So this is black hole mass versus sigma. The colored, the circles the colored points are the simulations. These are the observed points. You get the m-sigma relation out of this. And yes, we've chosen our fraction of how much energy from the AGN couples, and that gives you the normalization of this relation. But the slope is completely independent of that. If I change the one free parameter for our feedback model in the simulations, I just shift these predicted curves up and down. So the slope of that comes out naturally. And this is just an example of what happens to the black hole mass with and without feedback. Without, it just runs away until it exhausts all the gas near its radius of influence. And you can tune things such that you still get an m-sigma relation with no feedback, but it's one with a couple orders of magnitude of scatter.
Does that mean the slope comes from the potential well argument you made earlier?
Yes, so it's essentially reflecting the binding energy of the galaxy, of the baryons relative to the black hole. In detail, there's been some argument about whether, say, the fact that this is observed to be sigma to the fourth versus sigma to the fifth and what that implies. In detail, there's a lot of mess going on, both in terms of how our model in detail implements this, but also in that what really matters is the binding energy of the amount of material that survives within a given radius at a given time at the end of the merger. And so all that mess sort of blurs the distinction between those details. Marginally. Yeah. But again, the rates you calculate there are so super Eddington during the phase where this feedback matters that capping it at Eddington seems like a reasonable thing to do. I think it's still, you'd like to ideally have observations of things like Euler's and estimate are these things at or close to Eddington. I think the observations suggest they're at very high accretion rates.
I see. So you have the feedback put in directly into the gas dynamics, but then you also just by fiat said that black hole
Cannot go above Eddington. Yeah.
So if you imagine the depth of the potential well at the center of a galaxy, even though the dark matter density is very subdominant to the stellar and gas density in the region, the overall depth of the potential well should have a significant contribution to the dark matter, right? Compared to being unbound entirely.
Yeah.
So can you check to see? If you could look at to what extent the depth of the potential well correlates with these things versus dark matter halo mass, or
Yeah. So you can look at all the different correlations. This is one projection. If I wanted to plot the way we've put in feedback, the most fundamental correlation is that detailed combination of binding energy of a certain fraction of the baryonic material. And that reflects a combination of things like the halo. In terms of just simple correlations, black hole mass versus halo mass, yeah, you get a corresponding correlation. It's much messier, though, because in detail, the halo, yes, it contributes significantly to the central potential, but it does so in a non-trivial way. It's heavily affected by the baryons at the center. And actually, so I was going to just say, here's an example of all those different. You can project this in any quantity you want. Black hole mass versus sigma, dynamical mass, stellar mass, binding energy, effective, whatever quantity you like. The simulations, which are the black points, always give you something similar to the observations, which are the red points. And one thing you'd really like to do is, if these very general feedback regulation arguments are true, then it should be something like binding energy or binding momentum that is actually setting the correlation, not just sigma in and of itself. So you can look whether or not at, say, fixed sigma, is there a residual correlation of black hole mass with these other galaxy properties that would set the binding energy. Like residual black hole mass versus effective radius or stellar mass at fixed sigma, or at fixed stellar mass, black hole mass versus sigma or RE. And these are all observed systems. This was from a paper a few months ago that we wrote with Brant Robertson and Elizabeth Krauss. There's tentative evidence, and this actually at the same time, Monique Aller and Doug Richstone totally independently did an analysis that came to the same conclusion. There's a suggestion in the data of this. It's at 3 sigma, and if you really want to be careful and throw out every object where the observers had to do, say, a bulge disk decomposition or something sticky, this goes down to 2 sigma. So we absolutely need more data to say whether this is actually seen. But this is potentially a way to look for these trends. And if you just say from the data we have, what's the actual best, over all the variables we have, what's the best predictor of black hole mass? It's some combination of stellar mass and bulge mass that looks like binding energy. So basically, black hole mass goes as binding energy to some power that's close to 1. And this is just residuals of black hole mass versus bulge binding energy. The black points are predicted, and the colored points are the observed systems. There's no residuals in this space. So there's a suggestion of this tentatively in the observations. We certainly need more observations to say more robustly. And so this...
So, Phil, can I interrupt for a second? Go back. You originally said, earlier on, you made the point that you had the black hole blowing up the gas in its vicinity.
Yeah.
In the background of an already set spherical stellar hole. But there are claims by Peng and other people using HST, looking around quasars, that they see, and big massive black holes that sit in
at high redshift in small bulges.
So what's your take on
So some people have used this to say phrases like the black hole grows before the bulge.
Exactly.
I think that's a misstatement. I think another way you could say it and reproduce the exact same effect, so there are a lot of sticky issues with these observations that I won't get into, but if that's real, another way you could say it is simply that the normalization of the M-sigma relation evolves. The black holes are still coeval, but with a different normalization. And actually, this predicts something very much like what they see, because at high redshift, both because of halos being more compact, but also because everything's more gas-rich, bulges are more compact. And this is observed, that bulges at high redshift are more compact. So at a given stellar mass of the bulge, it's more compact, it has a deeper potential, a higher binding energy. So the black hole has to work that much harder to blow out the gas and would grow correspondingly bigger before it did so. So I've actually got...
Well, but it's a little funny because the potential, these things are not dark matter dominated.
No, I agree, but the increased gas fractions that you expect are sufficient to give you that just because they build a more dense stellar peak.
By the time these things make their luminous black holes, all that gas is turned into stars.
Yes, but the idea is that if you had very gas-rich systems and merged them, that 10% that typically makes up what was formed in the dense starburst might rise to 30 or 40%, so your bulge has a much deeper potential when the black hole kicks in.
But the stellar mass is what's contributing to that potential.
Oh, I agree, but
So then the stellar mass should still be on the...
for a given stellar mass, the potential is deeper.
It's higher,
Yeah.
because it's more compact.
Yeah.
But the stellar mass they claim is below, say, the Lagrangian relation. That's what their claim is. And that I don't think can be true.
I guess I don't see that. I think for the stellar masses they see, if the potentials are twice as deep at the same stellar mass, the black hole should be twice as massive, right? And that's my argument, is because at a fixed stellar mass, things are
Sure, they're more compact.
compact. Yeah. I thought I had a plot actually showing more or less what the expectation was for that, but I can't find it, so we can talk more about it later.
That argument, of course, is that those galaxies you don't see today.
Yes. I mean, you'd love to see those objects today, and I think this gets to where I think there's a local analog that you could look for weather effects like that can explain these things. So, unfortunately, I can't find the plot of the redshift evolution, but I can show you, relating to an earlier question, how this relates to pseudobulges, which are another class of objects where at the same mass, you might have a very different potential depth. So this is also from that recent paper by Josh Younger, black hole mass versus sigma for merger remnants with classical bulges and isolated disk galaxies that build by these instabilities pseudobulges. And you can see there's a pretty big offset. And I apparently just switched something in my talk while I cut away. Yes. Okay. Sorry, I switched to the wrong part of the talk. But in short, what's happening here is that for a given mass, for a given pseudobulge mass, because they're structurally very different, there's a different potential. And so you get an offset here. If you were to replot this, which is the plot that I think I accidentally deleted when I just cut out there, if you were to replot this versus the binding energy of the system or versus those more fundamental correlations, there would be no offset. And there's some tentative evidence in the local universe for this from a recent paper by Hu et al. I think there's a lot of objects out there that this data potentially exists or could be obtained for that would be useful to test these, as well as just trying to find maybe not true high redshift systems, but analogs of those high redshift systems, very compact ellipticals, and seeing where they lie on these correlations. So let's talk about the feedback effects itself in the last few minutes of this talk. Where does this energy and momentum go? You can get these outflows. This is just a velocity map in the simulations of the gas flowing out. There's an important point to be made, which more or less confirms the conventional wisdom, but is worth making. This is the ratio of the black hole feedback energy to stellar feedback energy with a simple prescription for stellar-driven winds as a function of the mass of our systems. And the point is, I can sort of rescale these normalizations by playing with my prescriptions, but qualitatively, you always get this trend that even in violent events, let alone over the lifetime of a galaxy, the starburst feedback is more important at low masses, and black hole feedback is more important at high masses. This is from a paper by TJ Cox. It should be out in the next couple weeks. You can also make predictions for the detailed properties of these outflows, where this is some examples from Deshka Narayanan's work, where he's made models of the CO emission, for example, and you get these sort of clumpy structures. You can look at the predicted line profiles, and they've got all sorts of fun features in them that are potentially indicators of how strong this feedback is and what spatial scales it's relevant on. This also has implications for the halo. I mentioned hot gas getting kicked out and contributing towards the halo. So this is a map of gas density and temperature in a merger. You saw this region just get orange here. That was just purely kinematic effects and stellar feedback. There, the AGN just lit up. You can see as this blast propagates into the ISM, it dramatically heats up the halo gas. When you go from this cold temperature to a fairly hot halo. And when you look in detail at what that predicts in terms of the entropy profile of the gas and the metallicity profile, you get something. This red line is with no AGN feedback. This blue line is with AGN feedback. This is the entropy profile. These are all predictions, all these lines, and all these colored lines and points. The dotted lines are observed non-cooling flow clusters. So you get a profile that looks like a non-cooling flow cluster. So this may be important, not in terms of solving the cooling flow problem at late times or addressing this maintenance mode, but it may be important in setting the initial conditions of the halos in which these systems will later live. If you made these massive ellipticals in the first place through these violent events, then these feedback mechanisms can be important in terms of how those halos got to their sort of pre-cooling flow conditions. And you can make specific predictions for things like the X-ray emission. This is just an example from another paper by TJ Cox from a couple of years ago, where without and with a black hole, just making a map of the X-ray emission, and two things are happening. It's the feedback's heating up the gas, and it's also kicking metals out to large radius, which pumps up the X-ray emission. And so the punchline that everybody wants to know is, how does this affect the star formation rate? And so this is star formation rate of an example with and without AGN feedback. The dashed line has no feedback. The solid line has feedback. Now, you get this dramatic difference. In this case, the trickle of gas that survives the merger, this thing's still forming stars at 8 solar masses a year, a couple of gig years after the merger. You'd never call that a red and dead elliptical. Now, to be fair, this is a fairly extreme case. I think some of the claims that were made on this, people got excited about fairly strong examples. So this case, the galaxies had a huge amount of gas. They were 80% gas, basically, at a year before the merger. And so a lot of it survived and formed a disk after the merger. So this may be very relevant at high redshifts, where you need to, where systems could be very gas-rich, and where observations suggest, even at Z of 3, there are already red and dead systems. And there, maybe you need something like AGN feedback to truncate this as quickly as you would then, especially since there's so little time by Z of 3 that your system had to turn red very quickly. At Z of 0, I would argue that this may be less important, and the simple reason is, if I rerun this with a system that has only, say, a few % of its mass in gas, then the trickle here that's predicted is much less. And yes, it will always cut off more strongly with AGN feedback included, but it is no longer clear that you need AGN feedback to get colors like observed ellipticals if you've got something like a merger already that consumes most of the gas just by star formation.
What's the spatial scale of that star formation when you don't have the AGN?
So a lot of this is happening in an embedded disk that's a kiloparsec or so in size. You get a lot of, you actually want some of the gas to survive because it helps you form kinematic subsystems in ellipticals that look like those observed. So there's some balance between these two, I think.
So Phil, how confident should we be that the simulations are reproducing the star formation histories correctly?
It depends on what you mean by star formation history. In an integral sense, I think you can be fairly confident because a lot of these details don't matter much.
I mean, in this kind of simulation, if you're saying that the starburst consumes the gas, that's
Yeah.
why it turns red. You know, should we believe the starburst?
I would believe that because essentially the starburst is the consequence of the gas losing its angular momentum, getting dumped into the center. You can change your star formation prescription. You're not going to change the answer that over a couple 100 million years that's going to turn into stars. It's very hard to avoid that gas turning into stars and still, let alone do that and still lie on something like the Schmidt-Kennicutt relations. The details of, how wide is this burst? What's the one question that you get asked a lot is what's the star formation rate enhancement from a merger? In other words, how high is this peak relative to the background? Those are more sensitive to the details of how you put things in, and I think the best we can do is quantify those as a function of our prescriptions. I'll just briefly mention that this also has a lot of interesting consequences for quasar light curves and lifetimes, basically in that the AGN itself shuts down in something like a power law fashion with feedback included and wouldn't without any feedback included. You can actually derive a very simple expectation for why that happens, just making some general assumptions. The AGN feedback happens on a small spatial scale relative to the galaxy, on a small time scale, and injects something like the binding energy. And that gives you analytically some basic expectations about how whatever outflow will behave and how it'll get gas out of the center. This is an example from the black line's a major merger simulation of how the AGN accretion rate decays after the peak, and this green line is the analytic expectation. The nice thing about that is that you can generalize it completely to very minor mergers. That was just a simulation of a very low mass ratio encounter, something LMC sized falling in that doesn't at all destroy a disk, but would still ignite maybe some AGN activity. And that produced this red line, so less luminous activity, dies quicker, but very similar qualitative behavior. And you can say basically that with scaled down amplitude, now here the amplitude of this is not strong enough to kick out this gas. You don't get that blowout. But in some small region around the black hole, the physics are basically the same. And that lets you say things about, very broadly, sort of the quasar lifetime. How long do you spend above a given luminosity? Where clearly this peak phase is short-lived. This more extended, lower accretion rate phase is very long-lived. And I won't go into the details here, but just I'll say that when you couple this to the observed quasar luminosity functions, you can get interesting answers because it's not as trivial as I think some models assumed in the past. If you just assume that every AGN turns on, lives a fixed amount of time at a constant luminosity, and turns off, then the distribution of black holes that are lighting up at a given instant in the universe looks exactly like the quasar luminosity function. You just change the normalizations on your axes. If that's not true, if you get something more complex like what we see in the simulations, it enables a whole range of different behaviors where you might have a system that starts down here as a disk, shoots up here on the luminosity function during the course of a merger, and then slowly decays back here. And you might see it down at L star as a K plus A galaxy, and then down here again as some low luminosity X-ray source with a decaying host. And this is just sort of a zoom in of where you expect these different populations to be important. And there are a lot of predictions you can make for what this scenario might say differently from simpler scenarios. I won't go into the details except to say that we've been doing recent work to look at how, for example, the clustering reflects this. There's interesting suggestions in that basically the observations seem to say that quasars here cluster the same as quasars here, which suggests that they're not just different mass systems each lighting up for a fixed amount of time, but that they're the same systems moving across the luminosity function. And there's other games you can play with clustering in terms of what host populations there are. I'll just mention there's some interesting suggestions. The punchline of this plot is simply that observations say that quasars have too many companions on small scales, which fits naturally in line if they're merger-induced. That's what this rise here in the data points relative to this black line is in the correlation function. But there's an interesting suggestion in a paper by Will Serber from last year that these black points are quasars, and this is their bias relative to their large-scale bias as a function of scale. So basically, this shooting up means there's too many quasars packed together in small groups. But then when he redoes this for Seyfert's, he doesn't see this trend. These are these open points that are hard to see. They're basically dead flat here. So in other words, there's no excess of companions in low luminosity systems. There is in high luminosity systems. And I'd really like to get into more of the observations, but I think there's a lot of different ways that we can start pursuing this, and that are really all just at the very nascent stage right now in terms of probing where these distinctions happen. But I hope that I've given you at least a sort of overview of what we think is happening in terms of the competition between all these different fueling mechanisms and effects, and how that basically all flows from the fairly simple assumption that black holes regulate their growth in accordance with the M-sigma relation. So thank you very much.
So you didn't really talk about how you seed your black holes when you're doing cosmological simulations.
So for cosmological simulations, for a lot of these simulations, we're studying idealized cases where we smash two disks that we prefabricate together. And that lets us study how this depends on everything in detail. You can't run 500 cosmological simulations to see how it depends on your feedback prescription. So for the idealized simulations, it doesn't matter if we seed it with just an arbitrarily small black hole, like 10 to the 5 solar masses, or we put it initially on the M-sigma relation. Basically, we get the same behavior. For cosmological simulations, say we have done experiments where we try to simulate, say, a Z of 6 quasar. There, especially for the very high redshift systems, you do have to think more about seeding because, and this is well known, that those Z of 6 quasars are 10 to the 9 solar masses at Z of 6.3. How do you get there that fast? There's problems if it's just even Eddington limited in the whole time up to there. It still requires it be 200 solar masses at Z of 30 or something. So there, it's dicier, and I certainly wouldn't claim that we're resolving or modeling the formation of the seeds of the intermediate mass black holes or whatever you think.
But you feel confident that the M-sigma relation that you find is independent of seeding?
Yeah, basically we can play with what we want with our seeds. There's enough gas flowing in. It's such a small amount of mass that actually needs to be added to the black hole that you always can jump up to the M-sigma relation. Where I would expect that to break down is only at the very lowest masses, below, say, 10 to the 4, 10 to the 5, where you may be looking at things that are, in effect, the seeds for later formation and are first getting to that point. And B, if you look at the Bondi scaling, it goes like m squared. So at those low masses, that m squared term starts to kick in pretty significantly.
This fact that you cut off the luminosity at the Eddington doesn't affect the mass then at all.
Yes, so you should, well, no, sorry. So
Or does it? Is that a key ingredient in all of
So that's a key ingredient in all of this. Sorry, yeah, because if you're allowed to be, because it's a fraction of the luminosity that's coupling. So if the system were, say, 10 times Eddington, then it would have the same then equivalent, you could say it's the same luminosity at 1/10 the mass, right? And so it would self-regulate. If the regulation is just based on the luminosity, it would self-regulate at 1/10 of the mass if it were 10 times Eddington. So that aspect of it is important. Observationally, I'd say the overwhelming evidence is that there is some meaning to the Eddington cutoff.
The other way I say is it wouldn't affect the scaling.
Yeah, it would affect the normalization. Yeah, we could
So you
play.
put 10 times as much mass on it, and
Yeah.
you still end up with the same M-sigma relation. For a fixed.
Let me put some of it in because you could have super Eddington accretion with Eddington luminosity coming out.
Oh, in terms of
You'd end up with the same mass.
yeah. So as long as that scaling were more or less on average constant across systems in terms of how super Eddington you were, we could get it would change the normalization for our current amount of feedback, but then we'd say, well, presumably some different fraction of the energy couples and renormalize everything. It wouldn't, unless systems were preferentially super Eddington at one end or the other of the mass function, it wouldn't change the slope of these correlations.